Hey everybody, so this video is going to be kind of an extension on the last video lesson on atomic structure, where we ended talking about the role that the electrons play in allowing one atom to interact with another atom. And when atoms interact via their electrons in order to join together, they are forming larger molecules through their chemical bonds. And this video lesson is about one specific type of chemical bond known as covalent bond. And there's actually going to be two different types of covalent bonds that we talk about just in this lesson alone. So for the first covalent bond, we're going to make another drawing of a carbon atom. So I'm actually going to start just like we started the last one with some green. I'll skip a few steps here and let's just put inside the nucleus 6 plus, representing 6 protons. Okay, and that tells us that we're dealing with a carbon atom. If you want to be complete, we could probably just accompany those 6 protons with 6 zeros or 6 neutrons if you wanted to. And just like in our last video, we could circle all of those inside the nucleus of this atom. So there we go. There we have another carbon atom nucleus. And I am going to go ahead and draw around that carbon atom its first electron orbital. And I'm going to draw around that carbon atom its second electron orbital as well. And then just like we did in our previous video, I'm going to give the first electron orbital its full dosage of 2 electrons. So there they both go. Okay, and then I'm going to give the outside, the outermost electron orbital, the valence orbital here, its remaining electrons, which there should be 4 left. There's 1, there's 2, there's 3, and there's 4. But you might remember from our previous lesson that there's this rule that exists in atomic structure called the Octet Rule, which basically says in carbon here we have these 4 valence electrons, but this valence shell actually wants 8 total electrons. So what that means is, yes, it's great that there's 4, but really there should be a total of 8. So we're missing an electron here, and we're missing an electron here, and right there, and right there. So all of these places should have electrons if this carbon atom is to fulfill its octet rule. So carbon is a really good covalent bonder to other things, which means it is going to attract other atoms because it is searching for these 4 remaining electrons that will satisfy its octet rule and give it 8 valence electrons on the outside. So one of the things that carbon is really good at covalently bonding to is something known as hydrogen. So if I switch back to drawing protons here for a second, if I draw a hydrogen atom's nucleus, it is basically 1 proton. Okay? And to balance that 1 proton, a hydrogen atom also is composed of 1 electron. But to make sure that we don't get this confused, let's go ahead and let's loop that electron in with that positive charge. So there's a hydrogen atom. Okay, and then I'm actually going to go do the same with the rest, the other 3 sides of this carbon atom, so to speak. So let's just say there's another hydrogen nucleus here, another hydrogen nucleus here, another hydrogen nucleus there. Okay, again, hydrogen just has 1 proton in its nucleus. That's its defining characteristic. And because it has 1 proton in all of those nuclei, it also has 1 electron. So let's make that hydrogen's electron. Here's another electron from hydrogen. Here's another electron from hydrogen. And just so we can try to keep everything straight here, let's try to loop that electron around that proton to show that that's our hydrogen atom there and here as well. Okay. So what we've just done is we have these unique hydrogen atoms that each have 1 proton and 1 electron on all 4 sides of the carbon. And what's interesting about hydrogen, or what makes it a little bit different from carbon, is we don't even get outside of the first electron shell. And you might remember from the previous video, the first electron shell can actually only hold 2 total electrons. So hydrogen is actually, since there's only 1 electron in its outer shell, it's missing an electron to fulfill its maximum of 2, and carbon in its outer shell is missing 4 electrons to fulfill its maximum of 8. So we get into this really, really convenient situation here where the hydrogen atoms and this carbon atom can share their outermost electrons to create a situation where all of the atoms have their valence electron shell completely full. So let's take a look at what that means and see that that in fact is the case. And I'm going to use a slightly different color here just to try to keep everything straight. So if we go back to the top of this carbon atom, we see that it's got this one lonely electron, but here comes a hydrogen bringing another electron, and now these two electrons here together sit in a pair. Same thing is going on this side of the carbon atom. We had the carbon electron, and here's the hydrogen electron, and together they are making this pair. And we have a pair of electrons, one from hydrogen, one from carbon down here, and we have a pair of electrons, one from hydrogen and one from carbon down there, or over there on that left side. And what you see now, if you were to count all of this up, that the outer or the valence electron orbitals of these different atoms are completely full, and those atoms therefore are stable as a result. So if you count now all of these electrons, there's a pair there that's 2, there's a pair there that's 4, another pair there is 6, and another pair here is 8. Carbon has now fulfilled its octet rule. There are 8 electrons surrounding that carbon atom, so it's good to go. It's satisfied the 8 electron maximum in its valence electron shell. Similarly, each one of these individual hydrogens, again, if you consider the 2 electrons that are together inside these purple circles that I've drawn, this hydrogen atom at the top has 2 electrons to satisfy its outer shell. This hydrogen atom on the right, 2 electrons, hydrogen on the bottom, 2 electrons, hydrogen on the left, 2 electrons. So both the carbon and the hydrogen are full in their outer shells and have a maximum number of electrons, which makes them very stable. And notice what has to occur for that to take place is a situation that we call really, I guess, 2 things here, a non-polar covalent bond. And in a non-polar covalent bond, we have a situation where atoms share their electrons equally, and that's the important part here. That's the important part. They share their electrons equally in order to fill their valence shells. So that is a situation of a non-polar covalent bond. Really what covalent bond means, if you go all the way back up here to the top, we're talking about covalent bonds, and covalent bonds are all about sharing electrons in order to fill valence shells. And in the case of a non-polar covalent bond, right, what non-polar means is that those electrons are being shared equally by all the atoms that are involved. But there's a slightly different type of covalent bond that is important for you to know, especially in the case of biology as well. Okay, so a little bit different set of atoms here, at least one major atom. So I'm going to go back to drawing the nucleus of that atom really quickly. And in the nucleus of this atom, instead of having 6 protons, we are going to have a total of 8 protons. Which means, just for the sake of completion, I guess we can go ahead and put in there 8 neutrons. Okay, and we can then start to fill in our electrons as well. So let's say, okay, there's the nucleus, and then we have our first electron shell, which is going to be full of 2 electrons, and then we have our outer shell. So remember, if we have 8 protons and 8 neutrons, likely we are dealing with the situation where we filled up, oops, sorry, that needs to be red. We filled up our first shell with 2 electrons, okay, and then since we've already used 2, we got to get to 8, so that means we need 6 more. So what we can do here is we can say, okay, here's a pair of electrons, 1, 2. Here's another pair over here, 3, 4. And then unfortunately, we're going to have an electron down here without a partner, and we're going to have an electron over here without a partner. And if you count up all those electrons, sure enough, there's 8 electrons to match our 8 protons and our 8 neutrons. This is an atom of something that you might know as oxygen. Okay. And oxygen, poor guy, is missing a couple of electrons. It's missing an electron it could really use right here in order to pair up with that lonely electron, and it's missing an electron right here. Well, guess what has 1 electron to share? It's our friend from over here on the other side, hydrogen. So if we bring in a hydrogen atom here and a hydrogen atom here. And with that one proton in the hydrogen atom, we bring in the one electron and the one electron, and we kind of loop them together so we can see that they belong together like we've done before. Then we've created a situation down here at the bottom where there's a sharing of electrons, just like we saw in the covalent bonds over here when we made this hydrocarbon over here on the left-hand side. Okay. So now if you were to go around and you were to count hydrogen, both hydrogens have their 2 electrons, so they're happy. And this oxygen atom now, through this sharing relationship, also has fulfilled its octet rule. It's gotten to a total of 8 electrons in that outermost electron shell. Here is the kicker with this now molecule, which I'm sure you can recognize if we say that this is an H. This is an H, so those are both atoms of hydrogen, and this is an O. You can see we're dealing with H2O, or other words, water. There's something that's a little bit tricky about this particular type of covalent bond here. And the situation that we find ourselves in now is oxygen is a really, really, really big atom in relationship to hydrogen. It has 8 protons where hydrogen only has 1 in its nucleus. So because it has 8 protons, oxygen actually has this pull, this effect on electrons. The positive charge here inside the nucleus of this oxygen atom starts to pull the negatively charged electrons in this direction from that hydrogen, and starts to pull this electron pair in that direction. So we get this kind of tugging of the electrons by the protons in the oxygen atom, and what that causes is it doesn't quite cause this sharing to be broken, but what it means is that the oxygen actually hogs those electrons in that pair a little bit more, and the hydrogen is kind of losing them a little bit. And the consequence then is because oxygen is kind of pulling more electrons toward it, the oxygen side of a water molecule becomes slightly negatively charged. And because these hydrogen atoms are kind of losing their electrons, or the electrons are being pulled away by that proton-heavy nucleus of the oxygen, these hydrogen atoms take on a slight positive charge. So water molecule is what we call a polar molecule, meaning on one side you have a negative charge, and on the other side you have a positive charge. You have 2 poles, just like the Earth has a north and a south pole. You have this separation of positive and negative charges because the oxygen is wanting to hog the electrons. Even though they're being shared unequally. And that brings us to our final definition, which is the definition of a polar covalent bond. And a polar covalent bond, very similar to a nonpolar covalent bond, it is when atoms share their electrons, because that's really just the definition of a covalent bond, atoms sharing electrons, but they share them unequally. That's the major difference here. They share their atoms unequally in order to fill their valence shells. So here you go. There's a good comparison of 2 types of covalent bonds that you will need to know in order to understand biology a little bit better. On the one hand, you have the nonpolar covalent bonds where electrons are being shared, but they're being shared equally in order to satisfy the valence shells of all the atoms involved. But in a polar covalent bond, those electrons are being shared unequally, which causes the molecule that forms as a result to have a slightly negative end and a slightly positive end, which, as you'll see in a little bit, is something that is pretty significant to sustaining life on our planet.